compared to what it could have been.
So, how do you feel about homework? Ready?
Go ahead.
Book online, find assignment, ask friends due by midnight today. If you're interested in the frame. No information, I don't care, it's just a question. Okay, think we match? Okay. Those I've seen look reasonable. We are, what are we doing?
Predicting future.
Perfect. Future of whom?
An electron that got robbed.
Huh?
An electron that got robbed.
Okay. That's also true. Rob, in which sense? What was Rob from reality?
As I say, it lost its friend at one time.
Okay. So we are looking for localized electron, and we are looking where how it will its distribution in space will develop in time. And you already developed some scientific hypotheses what will happen to you, right? So according to your expectations, what will happen if you have a distribution of a certain width and overall distribution moves somewhere with certain momentum?
Continue to move while spreading out.
Yes, spreading out. Yes, that's right. So there is nothing more novel in a couple of meetings. So we just work to support this hypothesis and derive some consequences. So it will be great if today we complete so-called uncertainty relation. So we are going through modeling of applying our protocols, our methods to predict future to one relatively realistic problem, simply realistic problem of this electron which is covering the universe. And as we go through it, we will find some common observation that will be applicable to any quantum system, to electron anywhere. And this conclusion will be so-called uncertainty relation. So, any ideas what do you? Yes?
That you cannot know the exact position and momentum of it.
Okay. And what is certainty and what is uncertainty? So Ben was correct. It's common knowledge, same as I was really impressed that you guys are well aware of Schrödinger cat. So I'm also impressed by your knowledge about uncertainty. But we are, this is absolutely correct, but we need to, well, basically what we didn't do in this course, we translate things between human language and mathematical language, for example. So we need to define what is uncertainty. And you already know the answer, it hooks in your heads. You already started dealing with it, although you may have noticed. We discussed it within the last 5 minutes. So an electron with momentum and some distribution moves. So distribution is characterized by width. Right? So what does it mean, width? If it could be certain localization of an electron at a given Cartesian point, the distribution will be infinitely high and infinitely thin, right? But if it has probability to be a little bit to the left, a little bit to the right, maybe not a little bit, it has distribution, it means position is uncertain. It's probabilistic. And the width of this distribution is mathematical measure of uncertainty. So we are going to mathematically define uncertainty of position, uncertainty of momentum, and multiply them by each other. And then if Ben was correct, their product will grow with time or stay constant with some constant larger than zero. So both uncertainty of electron, uncertainty of position and uncertainty of momentum are finite values, and their product is finite value as well. Which means one cannot measure them, one cannot know certain position or certain momentum simultaneously. Okay? So if you got this idea, you are done with today's meeting. The rest are mathematical details for your pleasure and homework. If you have taken notes, verbalize it by your own words. You can do it probably better than I. Okay. So we are going through the list. Everything above is what is completed. Everything below is what we need to do. Here is the homework that is due on coming Friday, and very natural and healthy if you have some questions. So I'll give some notes and instructions. Technical support. Yes. We ask you to project camera on another screen or as a subunit. So Wednesday night we will talk about homework as well. So focus on. So one of the homework assignments is to represent this function. See, it is not continuous, it has some breaks. And breaks are not good for taking derivatives. Therefore, to avoid it, one can represent it as summation of continuous functions, sin and cosine, with specific coefficients. And the procedure to do it is very standard. You take the function, multiply it by the basis function, which is either sin, integration, or here is the index of your basis function, here is the index of coefficient. While integration from minus infinity to plus infinity likely will lead to infinity and will have no sense. But everything repeats. If you remember a previous slide, or if you have printed out this homework, this discontinuous meandering function goes up and down with the same period. Therefore, it would be reasonable to perform integration not from minus to plus infinity, but from the beginning of the period and end of the period. Okay? From 0 to 5. And then your normalization will be 1 over L. So if you enough for now. We'll probably go over more details in the Wednesday night. But you see that those functions, trigonometric functions that approximately follow this pattern, minimum and maximum, will give larger contributions to expansion coefficients, and those that go out of phase will give 0. And we're not going to be crazy. We will consider only few elements with small numbers. Otherwise, it will get For the third homework assignment, third problem in homework 2. In the class, we assume that we base our future consideration on the answer. We assume that you have already got it. So we discussed it last time, Friday, right? So the answer should be k squared sigma squared to the square root of pi sigma. And the procedure of taking this integral is related to taking finite integral of the Gaussian function. Please raise your hands or give secret signal if you know by memory what is the finite integral of Gaussian function. What is the secret sign? So no one wants to. Anyone has an idea, like if one needs to go to the blackboard and find the answer. Do you know how to do it? So what is the problem? Why? Well, I'm drawing some time from lecture material to the things, but there is no sense to go quicker if we miss something wrong. So, what is the problem of taking integral like this? Would you experience problems if one remove the square sign? Not a problem. Just good sense if you can take integral of e to the minus y. Okay, good. Everyone. So this square is a bad guy. So this integral, if we remove definite limits, it is not analytical. There is no answer in standard equations. So it is one can take it only in from minus plus infinity, but it is so important because grades in freshman quarters follow natural distribution, all uncertainties follow natural distribution. So integrating this doesn't make sense. So it's a very, very popular thing. So popular that it was present in German moment. It is a trick. So the answer is square root of pi. And you can find it online in Wikipedia. If you look through chart of equations that I distributed, you'll see it. It will be there. But what if you wake up one morning and found yourself on the inhabited island, and suddenly you need to take an integral of this function? So how would you do it? It's a beautiful and elegant derivation, and I'm going to show you. So before we dive into this mathematical details, and we may postpone some material if we do not fit into today in the next lecture, but here is the expected last equation. So if we define width of this Gaussian wave packet in a free space, width, uncertainty of position, and uncertainty of momentum, and we consider that this wave packet develops forward in time according to Schrödinger equation, according to our ways to the future, we will find that it's equal constant square over 2 plus something that goes quadratically in time. So it is interesting that uncertainty doesn't get smaller, it's always increasing. So the life of electron always become more and more uncertain. It's like a law that Ben has formulated for it. Okay. And this is a very short equation that we will spend time in deriving this order of efforts. We will get this answer by processing the last equation from previous time, just a little refresher. So you did a surprise quiz where this box was staying for yes function. This box this one was staying for yes, accumulation of phase, but the factor that determines the accumulation of phase is eigenenergy of this wave function. Okay, and everything else is expansion coefficient. How much this wave function contributes to the overall effect of definition. And after we plug in all these things, we need to deal with this element, this zoo of functions. But if you carefully look onto this equation, you can identify that it has more or less standard shape. So there are 3 exponentials, and 2 of them have powers of k squared, in case independent variable. So one can merge everything that factors in front of k squared. And another thing, factors in front of k. So it can be another thing. We can summarize this equation in the form like exponential to the power minus a capital K squared minus g capital K with some factor of factors. If you are doing, right now, questions, objections? So right now, we are going from K space to X space. And I will try my best to show it in details. In your homework, which already has the answer is known, you are going from K space to X space. So it's same type of mathematical problem, you just go backwards. So by all mathematical challenges, it will be the same. So in some sense, you just repeat what you do in class with different notations. Okay? Yes?
Is the capital C supposed to represent the C in front of the integral?
Yes.
Okay.
Yes. It's I can't plug in this. It should be either lowercase here or uppercase here. Yes.
Okay.
So when we take this integral, we can plug in these factors. But right now, what I wanted to say, when you will be doing similar thing in your homework, you can write it down on a separate piece of paper and call it okay. This equation is more detailed notation, right? But now we do not care what they mean. We just take them as constants because they do not A and B do not depend on independent variable, and we just process this integral. Who never played strategy computer games? So most of you did. And well, there are standard traditional games like chess, but for modern generations, sometimes they are too boring because when your symbols are moving, it's fun. And if you spend sufficient time in playing, you know that you always need to find bypasses if you want to win, right? Some tricks. So here, same thing. We are learning a couple of these bypasses, but people who were deriving it at the first place, they were looking for things to how to simplify life, how to make it by spending less writing, less sheets of paper. So substituting and processing some long variables constants is one of the tricks, but there will be more. What is integral of a function in graphical sense?
The area under the curve.
Right. So we have the Gaussian function and we need to compute the area under the curve. And the answer will be square root of pi. I stopped doing it, but in the past I was trying to give the same class and hiding all important information until the end and say, what a surprise, and then give the answer. But you are it's what to expect. So here is it's not part of physical chemistry. It's maybe part of the calculus, but if you are not reproducing the integral of Gaussian function by immediately, you may enjoy it. It's really, I'm just checking the microphone. You may enjoy this derivation. So we do not know how to take e to the minus y squared. Typically, people try to make things more simple, but here the way is to make it more complicated. So suppose that we need to take not one of these integrals, but two of these. One along x dimension, another one along y dimension. Right? Integral 1, integral 2. Since x and y here are independent variables, if we take these integrals, multiply them, and then take square root of them, it will be the original integral that we need to take. And it is definitely from minus to plus infinity. Okay? Now, this integral I squared is to the power minus x squared of y squared. Right? No tricks. It's just a thing. Adding together two exponentials means summation of the powers. But in the geometry, x squared plus y squared square root will be distance or length of a vector. So you can call it r squared. And here is the infinitesimal increments are dx dy. So we are browsing in the two-dimensional space. These x's are okay. And we are multiplying e to the power minus distance from origin times area of this piece of area, right? So it's integral of e minus r squared over d. No objections.
You added the second integral. Is that because you combined dx and dy into dA?
Yes. Well, I'm not. I didn't disclose the trick that I'm going to do on the next slides, but in orthogonal Cartesian coordinates, this integral is complicated. But there is a more comfortable system of coordinates, so-called polar coordinates, in which this integral is much easier to take. Okay? So, and polar coordinates can be defined only in two dimensions. Therefore, we go from one dimension to two dimensions. So, we are solving for the same problem in geometrical sense. We are looking for integral of e to the minus r squared multiplied by infinitesimal area. But we can redefine system of coordinates. And we already did it probably when we introduced complex numbers, right? Instead of x and y, real and imaginary, you can define the length and angle, right? I do not need to repeat it. There is a polar system of coordinates for points and then instead of x and y, point on the point is determined by distance from origin and the angle. So if we go into new system of coordinates, the element of area needs to be defined differently. So we need to convert dx times dy into something depending on increment of distance and increment of angle. Do you know what it will be? What will be the small area in the angle of increment of distance and increment of angle?
R squared.
Huh?
Pi r squared.
Pi r squared. Yes, you are right in a sense that the whole area inside a circle of radius r will be pi r squared. Yes. But what if we look at the circle, this pi r squared, and then make a sector, right? And in this sector, look for a segment with only small dr. So what will be the area of this field area? If we are in Cartesian coordinates, it's small square is just dx times dy. But if we are in this polar angles, it will be something different.
R dr d theta.
Perfect. Anyone wants this explanation, or it is clear for everyone? Do not hesitate. So instead of dr d theta, one needs to multiply it by r. So if you look on the area and then make derivative over position, it will be length, circumference. And if you take derivative over angle, this 2 pi is when you take derivative over angle, it will be the only thing left will be distance. Therefore, increment of the area will be r divided dr. Bring up this question if you're not happy with it on Wednesday night, because you need to practice it again for yourself and some other problems. Okay, and now we are taking this integral. So e to the power minus r squared dr d5 r changes. So before, when we were in Cartesian coordinates, we were going from minus to plus infinity. Now we are covering the whole plane with radius never going less than 0, right? It's just distance from the origin. But angle spans from 0 to 2 pi to cover the whole space. So integration over dr goes from 0 to infinity, integration over phi goes from 0 to pi. E to the minus square r. And we can take integral over angle right away. You can see integral pi from 0 to pi will be just by factor. And we are left only with integration of r times e minus r squared dr. So, anyone would feel comfortable taking such integral? Okay, I see one sign. Anyone else? So this is somewhat easier than the original one. So in addition to this Gaussian function, it is multiplied by r. Right? Therefore, we can submerge this r under the sign of differential. So we can redefine the variable of integration. Is it clear what I'm talking about? Let me do it. Sacrificing time, but it's better to cover. So integral square. So we can first practice little integral r dr, which will be. Do not tell me that you do not know what the answer.
R squared over 2.
R squared over 2. What will be, again, if we go backwards, if you take differential d of r squared over 2, we will get this integral back, this under the integral. So therefore, we can make it equal to the integral of d r squared over 2. And now we can call this r squared over 2 a new variable, u. So it will be integral of du, with understanding that it is redefined. I know it looks not straightforward, but then life becomes easier. Now, if our u is defined as r squared over 2, it is easier just to put u as r squared and then multiply 1/2 the front. Then our original integral can be recast as integral e to the minus u times du and then 1/2 the front. So by making tricks by changing variables, we go from complicated integral to an easy one that each of you can take, right? So we take integral in the favorable system of coordinates in the favorable variable, and then return back. And we are kind of wasting time for that class because this integral of Gaussian is known. You can always find it if you do that. We better make sure that you know where it comes. So 1/2 pi integral du of minus u will be same function e to the minus u, right? This minus constant. So integration doesn't change this exponential. And then we need to evaluate this e to the power minus u at the limits 0 and infinity. So what will be e to the power minus u at infinity?
0.
0. What will be e to the power minus u if u equals 0?
1.
So 0 minus 1, minus 1. And another minus is inherited during the integration. So it will be 1 times this pi that is inherited from integration over angle. So I square that we defined originally will be equal to pi. And I will be equal to square root of pi. And I is originally defined as integral from minus infinity to plus infinity e minus y squared dy. Square root of pi. Okay? So anywhere, if you see and bring your function into this functional form, you immediately get the answer. So in the rest, our goal is to convert whatever our complicated construction is to such simple form. More tricks. So we are going from chemistry and physical chemistry to the pure math. I promise we will return to science. This is the integral we are taking. The C, A, and B are defined with something with physical meaning. This integral somewhat differs from standard Gaussian integral that gives square root of pi, right? But for those with experience in calculus and other subjects, it shouldn't, for all of us, it shouldn't be a problem to recast this integral into the form integral minus pi squared dy. There are ways to convert it, and price for such conversion will be just accumulation of some constants upfront. So this trick will be based on identifying full squares. So we are going to redefine integration variable once again, and it will be based on, how do you call this equation? Or we just memorize it without name.
Addition.
Full square, right?
Yeah.
So if you have, I know in some languages it is simplified multiplication. It's not simplified, but so this algebraic equation, polynomial equation. So if we can identify full square in here, we can redefine new variable as a plus b. And then tell that we have defined y squared. So our a capital can be considered as square root of a squared, right? So we can consider that a k squared is just little lowercase a squared. Okay? So the goal is to bring this integral into this form by making it to the exponential to the minus something squared. So we need to identify full square. And the thing that we are allowed to do to keep C is to divide multiply by the same factor or add and subtract same term. So this can be our lowercase a, right? If we define lowercase a in this shape, then the second term in front of linear k, we need to identify a times b. But there is only b capital. What if we multiply and divide by the thing that we have already defined as a lowercase? Then we already have our lowercase a, and the rest, this b capital divided by square root of a, will be p lowercase. I would prefer to write it line by line myself, but then we will die of time. So in our polynomial equation, a plus b squared equals a squared plus 2ab plus b squared, we already have two first terms. We have a squared and we have 2a times b. That's it. We don't have the rest. But in order to identify this b squared and complete the plan of simplifying the integral, we do need to have exponential to the power of this little b squared. But if we multiply and divide overall expression by the same factor, nothing will change. So we multiply by e to the power this little e squared and divide by e to the power. Divide means putting minus in front. So we are legitimate. We are allowed to multiply by these two factors. We know that these two factors will cancel each other. Means identity, means nothing. But we are bringing it here because of expected benefits. So it is our equation for the function for predicted future. And now this is a squared, this is b squared, and this is 2ab. And this will be factor which is like penalty, punishment, or how to say, price for identifying full square. So it doesn't depend on our integration variable, and we will keep it together with c coefficient upfront. So it will not participate in the integration. Okay? So what we have now is integral dk e of this full square times e to the square. Tired? Exhausted? 4 minutes. Probably it will be one lecture less in this semester because, well, there is no reason to go. I will complete. We convert it as a full square, a plus b, and this will be our answer. So our a plus b should become our independent variable. But how does a plus b relate to k? We need, if you change variable in the function, we also need to change integration variable. So we need to cast k in terms of a plus b. We need to find their connection. And if you will do it, time is up. We will identify that this thing is just e to the power minus y squared, and under y I understand this a should give us square root of pi. And we will to the final answer that we need for wave function. The physical things that give contribution to the final answer will follow from the coefficients that didn't participate in the integration. C square root of a and e to the power b squared. So one needs to be very meticulous and plug in back the definitions of all these coefficients. Right? We define it at the beginning. So B depends on position, A depends on time, and here are the rest of the definitions. This is simple, but it's sometimes it's like 15 minutes of work for it. And if we plug it in inside, so time is up. Wrap up. If you plug all things inside, you will see that wave function of the future will have some factors in front, but in essence it will look as Gaussian function minus x squared divided by width parameter that does change with time. With all these factors coming in. The last mathematical challenge, much smaller than we had before, is that increment of width will be imaginary, which is very uncomfortable. So the imaginary unit equal to this height. But who cares about wave function? It's not an observable. If you look on the distribution, we need to wave function star multiply by wave function. And if you do this operation, if we multiply star deflection, probably it will be star deflection as well. So if we will multiply a wave function by its conjugate, then the imaginary unit will disappear, and one will see that for probability distribution, it is Gaussian function with squarely increasing width. And this function of width, I'll skip something because otherwise we will not have time. If one take this width and multiply it by width for the momentum, then one will see that it increases linearly. Okay, we're probably exhausted. See you on Wednesday. I'll stay here for a few minutes if there are questions.
Can you go back to the completing the square?
Huh?
Can you go back to when you were completing the square?
Yes. Just a second. Daniel? Here or for
See ya. Go back another one, please. There we go. This is what I got last.
so it's where there was connection.
Yeah.
Yeah, well,
after a little bit, I think I got it. I just need to see where you multiplied because
Okay.
I didn't get how you got some.
And I
square,
did
but-
send you notes before, and I will send those.
But I'm right here and thinking about it. So
Please, please, please.
Email you the homework.
Okay, yeah, thank you.
Thank you for giving me a chance to.
Yes, sir.
If we say a squared equals ak squared, then we have to cancel on this. Okay, I see how that happens. Oh, okay. Okay, I see. Okay, I see it now. That took me a second to figure out how you got. So the 2AB was confusing me because you got the
Just divide by 2.
yeah, and then I also was like, where'd the K go? And then I'm like, oh wait, it's gone because it was
Well,
divided.
I-
It was
I-
divided.
I didn't declare purple, but multiply divide by square root of k, and k was already there. So originally it was only b times k, and then we multiply and divide by square root of k, and multiply divide by 2.
But you just canceled the K out because it's math. Okay, really.
Well, this term should have k, but we can
No.
k is part of lowercase a.
K has to be part of lowercase a because that's what we declared originally.
Mhm.
So when you have it's basically k squared over k. In a sense, if you left all the k's in before canceling them out, then b would have to be b over 2. I see what you're saying. I get it. I got there eventually. You getting there, Bill?
No.
So it took me much longer to get it myself.
So
I'm trying to understand if AK squared is equal to A squared.
okay, what?
If AK squared equals lowercase a squared, then A over A squared.
I don't. Why is there an a squared?
Where?
Where you have the a term. Why do you have over a squared?
No, it's not here. It's just
Okay, I just ignored the 2, so that root a squared. Does that help you out?
I guess I understand the root A part. So then how do you get A times B and then what do you substitute for B?
So when we're doing, so you have the minus, it's e minus ak squared at the top originally. We have e minus ak squared minus bk. So you could also just say e minus ak squared times e minus bk.
E to the minus A squared times E to the minus BK is what you're saying.
Yes.
And then what are you substituting in for B then?
So what you're trying to do is you have bk, right? On the originally. So then you want it to be 2ab, right? Is what you're
trying to get?
To 2ab. So then if you have if you multiply it by the a term, you have to also divide it by the a term to keep it the same. So therefore, if you had, I don't have a pencil. Do you have a
But
pencil?
you can come here and either show on the board or right here by finger.
Alright, so
I see what you're saying.
so if you originally you're supposed to have a k right here, but you're also multiplying the a squared with a, so there should also be a k squared with a right here.
Yeah.
But you
cancel them out, so then
So now you also want 2. In order to get 2, you just multiply by 2, but then divide by 2. So in order to, so then b is just basically taking the fault for anything that we want to add and multiply at this point. So you just say anything that isn't the 2 or the a is b.
Okay.
And then if you do this right here, you're multiplying and dividing by the same thing, and it should become apparent if this is b, and we already have a minus right here and a minus right here, then we just want to keep this minus to get the a squared 2ab b squared.
Okay, so on the bottom here, what is this saying? Is that just completing what you're saying?
So yeah, on the bottom here, we have a squared and 2ab, right?
Yes.
So what
This blue layer is common. It's apart from my layer.
Okay.
So you have a squared and 2ab. So you want b squared at this point.
Oh, okay. That's what I was thinking. I thought this was one whole term, one whole expression. This is another expression. So this is one whole expression. Okay. That makes much more sense.
So
I probably should highlight it in yellow or whatever.
Yeah,
Or remove this comment completely.
Yeah, because that comment made me think that this was all one expression.
No, this is just a different layer.
Okay.
Right.
So then
squared. Then we got the 2ab, and then b squared.
use this one. So this is the b squared right here. Right? This is the b squared. You want to take the minus one because all of our other ones were minus so far.
That gets you positive.
That would get you positive through everything. So, or well, it would get you minus y squared. Because we're looking to get the minus y squared.
Yeah.
So then you just have this left over. Now if you continue on, the part I didn't get is how this stayed outside the integration, because I thought it was still under the integration.
So
Do you get it? Yeah, that makes
does
sense.
b squared depend on a? Does b capital depend on k?
I don't remember.
No, it doesn't. Does a capital depend?
I don't think so.
So you can.
Well, that's just a constant. Oh,
Yes.
okay. That's the. Yeah. It didn't click for me, but now it does, obviously. So, okay, that makes sense. Some smart guy figured that out.
These things are just that you feel more confident, but if you just formulate initial first equation in the lecture, I mean, for wave function, and look into table of intervals, you will be able to figure it out. Those are standard inputs.
So some of these are written standard in the problem.
Yes, yes. Okay. Just I wanted to bring you more confidence in how it was derived, so that you can redirect and avoid fear. Sometimes it's actually better.
Okay. Somebody said it's hard to insert the equations back into it. Does it just take a long time and it's a lot of simplifying?
Well, 15 minutes sufficient. But you know, if there are more than 10 singles in your equation, there is always a chance of human error to get plus, minus, and it's normal. So one needs to do it properly and solve it.
Okay, well, that's what I needed to know. Was I just you glanced over this a little too fast for my brain to process through all the math.
I'm in between of two pressures. One is to fit so much information in, and another is not to sacrifice quality.
Okay.
Because like one can maybe stop here for the whole class and spread over the whole thing, and then you will be so proficient in the basics. But then I will be criticized for not giving actual real life problems.
Okay. Well, thank you for letting us stay and figure this out.
Thank you for the interest.
Hey, by the way, there's free food outside.
Oh, is there?
Right now.
Cool. Thank you. Things do make a little more sense now. I wasn't sure on number 1 on the homework, but if answer more questions on Wednesday.
Yes.
Yeah.
Look online for Fourier transform.
Okay.
And it is very standard problem. If you haven't seen it, you will see it before variation in some other courses.
Okay.
I can scroll.
So you just kind of use that from the first part.
Yes.
Kind of plug
you
in.
See, you for A1,
Yeah.
you put 1. For A2, you just put 2. So multiply this function by a sign and integrate. And this function is 1 from 0 to L over 2 and 0
Oh,
to L
okay.
over 2. And so you skip the interval where it is 0.
Where it's 0,
you
and
just
plug in
use, replace it by
where it
1.
has the actual.
Yes.
Okay. Thank you then. Makes a little more sense. So.
Okay.
Thanks for your time.
Okay.